this isn't just a ground-based astronomy problem. The classic solution is just put your telescope in space. And while I'm a big proponent of putting telescopes in space, that isn't a solution to this. It's very expensive. You can't service them nearly as easily. The technology level of a space-based observatory is years, if not a decade, behind what we can do on the ground. And you don't even get around the problem.
Hello, welcome to the Space Policy Show. I'm Colleen with the Center for Space Policy and Strategy, part of the Aerospace Corporation. This is our last installment of a 6-part series on resilience. Other shows include building economic capacity with space futures, the weaponization of space, leveraging more innovative launch, and creating regional alliances in the Pacific for global security. Today, however, we feature one of our How Stuff Works formats. It's a sort of primer, and today's topic is resilient skies. Basically, how do humans balance the services and benefits of space activities with maintaining dark and quiet skies? And why do we care? So today, I am pleased to host Lindsay DeMarchi, policy expert with the Center for Space Policy and Strategy, focusing on civil space and regulatory issues. And we have Samuel Factor, a senior member of the technical staff here at Aerospace Corporation in the Division for Signal and Image Processing. Guys, thank you very much for being here today.
Thanks for having us, Colleen.
Yep.
So remember, everyone in the audience, if you want to learn more about resilient space, be sure to check out the entire series at csps.aerospace.org/Space Policy Show. Okay, let's get started. So first, Sam, I've got to ask you, tell us what signal and image processing from space is. What does that mean? And how does that give you a kind of special insight into today's topic of dark and quiet skies?
So my background is in astronomy. So I actually have a degree in astronomy. And so a lot of what I do for my day job is taking images from space and processing them, essentially removing background, trying to minimize noise sources in the data, and then extracting some sort of usable information to then pass along to someone who can do that analysis. So from the astronomy side, it's a lot of looking at stars. From my background, looking at planets. Now it's more Earth observing image data sets, but very similar techniques.
Right. So you have that background of looking out to the stars, but then there's also the idea of satellites looking down at Earth and having high quality images that need to be reckoned.
Yes, exactly.
Yeah. So Lindsay, how about you? You've actually got quite a background on dark and quiet skies. So can you give us a little synopsis of some of that background?
Sure, yeah. Like Sam, my background is also in astronomy and astrophysics. And it was around 2019 with the real takeoff of commercial space, I guess, so to speak, that I started thinking about what we now know as dark and quiet skies. Probably just to get the definition out front. Dark is to counteract some of the satellite reflectivity of sunlight back down towards Earth. And quiet is to address the unintentional radio frequency interference. And you can imagine that if you look through a telescope, which is a microscope, but instead of looking at tiny things, of course, looking really deep into space at a super magnified degree, then things like interruptions from unintentional light could actually pose a big deal. So I started thinking about dark and quiet skies as an astrophysicist, and by a series of very happy accidents, I ended up in the policy world working in Senator Hickenlooper's office on the Hill as a space policy analyst, and now, of course, work at the Aerospace Corporation on space policy.
Yeah, thank you. That's excellent. So you stole my opening. I was going to ask you what what is the dark and what is the quiet, you know? Because usually I think of you think of light pollution, and I always think of, you know, human activity on the surface of the earth, cities, basically, right? Street lights, lights on buildings, your car headlamps. But this is light pollution in of a different way. So I'm gonna go to Sam. Tell us what your idea here is. What is light pollution from above?
Yeah, so as Lindsay was saying, with this explosion of commercial space launches that's happened over the past few years, the number of objects in space in orbit around Earth has just essentially exponentially grown. A few years ago, there were only roughly a few hundred objects that you could see with the naked eye from the ground, and now it's in the thousands. So these objects pass through your field of view. They are reflecting sunlight, or if you're observing in the infrared, they're emitting their own heat, and they leave effects in your data, little trails, little streaks. If they're very bright, they can saturate your detector, completely wiping out any data that would have been behind that satellite. So it's a big problem, especially with the just severe growth in number of objects out there right now
Right. I mean,
and
there's
planned in the future.
right, right. And it's I mean, it might slow down a little bit as more and more proliferated systems get launched and kind of settle themselves. But I don't know how much it will subside. There's something like 10,000 satellites right now orbiting the Earth, and the growth has been 3 and 4 fold in the last 5, 6 years. So yeah, it's huge. So Lindsay, I'm going to ask you to comment on two things. First of all, talk about what Sam said with, again, it's that light pollution, but of course, I'm thinking visible light. Sam mentioned infrared. So tell us a little bit about that. How is infrared interference or interference into infrared light different than the visible light spectrum? And then what is quiet? Tell us what quiet is.
Sure, yeah. So to answer that in the cleanest way, I'd actually zoom out to talking about the entire electromagnetic spectrum. So most people don't really realize this, but radio waves are light. All of the waves we talk about are lights, and it depends on the wavelength or frequency, different ways of talking about the same thing. So really, really large waves about the size of a house and down to the size of a dinner plate are going to be our radio waves, and they can get really, really tiny down to X-rays that can permeate our body. And I have an intimate knowledge of the entire electromagnetic spectrum because my background as an astrophysicist was using each of these different parts of the spectrum to look at the same thing. So the best way that I could explain it is like if I was to look at a body with all of these different waves, I would see somebody's heat signature. If I was to look at them with infrared, I would see their bones if I was to look with X-ray, and I would see their skin if I was to look with optical waves. And when we look out in space, especially at stars, for example, it's like seeing all of these things at once. So if I was to meet a person that way, I could tell if they were nervous and whether or not they brush their teeth the same time that I meet them. So sorry to give you a really disturbing image, but
No, I love this. I love this. This is the biometric data, but it's only with lights.
yes, and it's only with light. Yeah. So this is to kind of also give you an example of why astronomers care, because as you can imagine, there's pieces of information that are only available at each of these wavelengths. Just like I can't necessarily use optical to diagnose whether or not you've broken a bone. Maybe I could if we looked at swelling or something. It's the same thing when we look at space, that there's just certain pieces of information about maybe a black hole that's buried deep inside an exploding star that we couldn't get otherwise. So how does this actually come back to thinking about satellites? Well, if brightness is the problem from reflecting sunlight, a super easy solution right off the bat is, what if you simply painted them darker? What if you simply painted all the satellites black? You could do that, but the same way that you and I go outside in like a black t-shirt and we immediately feel hot, it's because black is absorbing that heat. But like I just said before, that thermal energy that's radiating off, still radiates. It's just at a different wavelength that's not visible to our eyes. It's radiating now in the infrared. So it becomes a new problem for infrared astronomers who are looking at space only using infrared waves.
Now, this has actually been done, right? There has been commercial companies that, in order to try to um, help astronomers see better, they were like, "Oh, we'll just paint it black so that it doesn't reflect," and then it did kind of mess up other astronomers. Yeah, this actually happened. So the attempts are there, but
Yes, and I'll also say that not all of them are necessarily using paint. So some other things that we've seen, I guess this is kind of jumping ahead in the conversation, but some other mitigation techniques we've seen before actually just reflect the light in a different direction. What if instead of going towards the Earth, it reflected light back out towards space? So people have gotten very creative, and to me, that's one of the most optimistic and exciting parts of dark and quiet skies is that there's lots of room for really creative solutions, as diverse as the satellites themselves.
yeah, yeah. Because I mean, satellite operators love space too, right? I mean, we do want to do the right thing, hopefully. Sam,
Exactly.
do you want to comment on some of, do you know any other kind of, what other things are satellite operators doing to mitigate some of the issues, either in, anywhere in the spectrum, basically?
I mean, it's all about trade-offs, like we were getting at. So yeah, putting either sunshades to reflect the light differently, simply orienting the satellite in a different direction at different times when they know they're gonna be receiving that sunlight. Specifically for Earth observing radio wavelength satellites, so lots of weather related things. They can actually turn off the transmitters when they're directly over a sensitive site, like a astronomy related observatory. Um,
Okay.
so they're not just beaming this radio waves down and actually can damage the very sensitive detectors on some of these receivers.
Now you have, Sam, you've got a lot of experience at different observatories. I mean, if you were a satellite, especially I'm thinking the small satellites that, they're kind of the size of a loaf of bread and they don't have a lot of, it's not a lot of capability built in. So the things have to be quite simplistic. But if they had to turn every time they passed over a site, how many sites are we talking? Like,
Yeah, I mean there are a lot of different sites over the U.S. and over the globe that we want to protect these dark skies. And so yeah, it's a trade-off between what are the capabilities of a satellite to mitigate and is it actually an issue? So for a lot of these like CubeSats, they're not going to be that bright. In terms of just they don't have a lot of surface area to reflect sunlight. And they also aren't as capable to do those sorts of maneuvers. So again, there's trade-offs. Um, it depends what you can, what you're willing to do, and what the regulations are that you have to do, which unfortunately right now aren't very much.
oh
I'll
yeah,
also,
regulation. Go ahead, Lindsay.
so, sorry, I'll also add, kind of thinking about it from the opposite direction. One of the things that Sam mentioned before is that if a satellite's too bright, it can saturate your camera that you're, taking optical astronomy for example. You need to use a camera which is going to have a receiver in it called a charged coupling device or CCD. And these are the bane of Sam's existence because every telescope has a different CCD, or maybe they're made from the same company. And part of being an astronomer is to intimately understand the way the CCD works because every electron passing through that detector can do a number of different things. And learning what those things are, maybe it can be a spill over from one column into another, and now it looks like that star suddenly got bright, or something that's called a hot pixel, where just a single pixel or a couple pixels in the camera look like they're also, displaying astrophysical phenomena. So getting to know the CCD is one part of being an astronomer. And so when a CCD is saturated by light coming from a satellite, it can create these ghost effects throughout the CCD where one streak looks like six or seven or eight. Um, Another solution to dark and quiet skies is to advance CCD technology such that these effects don't happen. And that would mean a lot of advancements for the astrophysical community at large, because every telescope in the country, in the world, is going to rely on CCD technology. And beyond photographers and astronomers, I don't really know how many people are using CCDs or working on advancing that technology. So it could be a real opportunity to put R&D into something that, I mean, Sam, you could probably speak a lot better to CCD technology now, but that's another area of improvement I think that could benefit everybody.
Sam?
Absolutely. And just to add to that, there are uh, detectors that are in the more on the infrared side than in the visible light wavelength, where instead of just essentially having a bucket of light and you collect all of the light that comes in, and then when you're done with your exposure, you say how many photons, how many electrons did I collect? In the infrared side, some of these detectors do what's called reading up the ramp. So during your exposure, you're measuring how much light is actively coming in without destroying, without zeroing out that pixel. And that is used for noise suppression, but you can also take advantage of all of that extra data to remove artifacts like cosmic rays, like satellite streaks, and it's just a lot more data. So lots of different technology that can be advanced.
Yeah, no, interesting. And I know I've read recently in the news that we thought we discovered a new asteroid. Astronomers thought they discovered a new asteroid, but indeed it was a Tesla.
This is
Or
not the
or
first time something like that has happened, actually, Colleen. One of the most one of the things I found most intriguing about dark and quiet skies was that one time it was front page news that we discovered a redshift Z11 galaxy, which is when you start to talk about when you measure distance in terms of Z, we're talking extremely, extremely far towards like the origins of the universe. So Z11, I think at the time was maybe the farthest we'd ever seen at that point. I think James Webb has seen Z14, but don't quote me on that. Very, very, very far. It turns out it was a piece of space debris throwing sunlight, just shot like a nobody was tracking it, or maybe if they had, they didn't know that it was spinning quite the way it was. But even space debris glinting sunlight very quickly and rapidly can look like high energetic phenomena coming from a region of space. And if that region of space aligns with a galaxy, it's reasonable to think this galaxy just shined at us from Z11 away.
That was the aliens winking at it.
or on the radio side, there's the classic story of a fast radio burst that turned out to be some astronomers opening their microwave before it had finished the timer, and just they got picked up by the radio telescope that they were operating. And they thought it was a fast radio burst. So lots of different sources of noise that can be
Wow.
misinterpreted.
That's some sensitive equipment, right?
Absolutely.
Well, this kind of brings us into, you talked about, Lindsay, you talked a little bit about space debris and how that, even that, like, because, we're not tracking all pieces of space debris. We're, anything over, was it 10 centimeters, we can pretty surely see, but anything less than that. And this brings up, I guess, kind of ideas of how we can improve the chances of satellites not getting in the way of good astronomy using government policy, government regulation, government incentives, right? So the idea of, well, if there's not as much stuff up there, maybe we deorbit the small satellites a little faster after they finish their mission so that they're not up there reflecting more.
Right.
Sam, did you want to just comment on some of the government, on how government's weighing in? I'll start with you and then go to Lindsay.
There's a couple of different ways that they're coming about this. One you mentioned is trying to regulate how quickly dead satellites have to deorbit. There's also just generally tracking what's up there. And that's good not just for astronomy, but for general space situational awareness, making sure things don't crash into each other. So that's something that we're doing actively already. But passing that data on to astronomers for them to be able to schedule observations around where the worst areas of satellite glint might be for a given time. And that is, there's different observatories may be able to take advantage of that data in different ways. For example, the older, more historical sites where it's literally just an astronomer sitting at the telescope all night, picking and choosing their own targets, they might be able to take advantage of that data if there's a easy to use website, for example. The more advanced, larger scale observatories that are queue scheduled or robotically operated, they might even be able to just plug that into their planning, their observatory planning pipeline, where before they schedule an observation, they can check, oh, is there going to be some satellite that would actually affect the data going through our field of view. So lots of different ways to approach that.
Yeah, yeah, excellent. And so I know that in the US anyway, it's the launch licensing for the kind of a shorter deorbit time. Um, that's through FAA. But Lindsay, there's also some other things that that governments are doing to try to limit the pollution, I suppose.
Right. Yeah. So it's through the FCC that the satellite licensing will, well, try to bring it down in 5 years, not 25 years, I think is
Oh,
the
sorry, FCC. Yeah, yeah, sorry.
yeah, but the FCC is also doing something that's called coordination agreements with the NSF, National Science Foundation, and also industry. And you might ask, why the heck does NSF have anything to do with what we're talking about? The NSF, actually, not NASA, is
The National Science Foundation.
yes,
Yeah.
NSF, National Science Foundation, actually is the body that manages a lot of major telescopes in the country. So I guess before getting into policy, I had assumed that was NASA, but it's actually the NSF. And so they will reach agreements between those in industry looking to seek licenses and the FCC to say, try to do your best to mitigate dark and quiet skies concerns. And industry has taken this really far. I can think of off the top of my head at least 4 different companies, major companies, that have taken this on and started developing tech at cost to them. They don't get that subsidized. They don't have grants for that. They are doing that out of their own pocket, which is really remarkable to see. And in exchange, astronomers are promising to follow up with measurements to see how well those mitigations have or have not been working. And coming back to debris, the ESA, European Space Agency Zero Debris Charter, also has a shout out for dark and quiet skies. Because like you were pointing out before, Colleen, these issues are kind of interwoven with each other, debris and dark and quiet skies, whether it's glinting debris or also just general space sustainability. Even our own Office of Space Commerce here in the United States has identified dark and quiet skies as a part of space sustainability. So I would even take this up to kind of the largest level at the UN. This year, it was the first year that dark and quiet skies is an agenda item to be discussed at the UN. So definitely on everybody's minds, both in the US and internationally. One of my favorite facts to bring up is that France actually, as a country, has a 7th magnitude limit law. That gets a little bit tricky when it comes to implementation.
All right, you got to explain that though. You got to explain that for our audience. Yeah.
Yeah. Okay,
Magnitudes are a odd unit that astronomers have stuck to their guns on.
Yeah, there's a lot to unpack in that sentence. So I'm glad that you stopped me. Like Sam brings up, magnitude is a unit of measurement of brightness, and it literally comes from the ancient Greeks. So you can imagine explaining this to excited high schoolers and college students who are So thrilled to be learning about ancient Greece when they came to do astronomy. But it's quite literally a logarithmic scale that your eye works on. And I won't say more than that, but it's a measure of brightness that's based upon the instrument that is your eye. And seventh magnitude is just a way of benchmarking brightness. You could say first magnitude. So I think like the Big Dipper, for example, is somewhere around fourth magnitude. For reference, the moon is like negative 26. It's kind of all over. Not important. What is
And so France is limiting it to 7 magnitude.
Yes, thank you for getting me back on track.
Yeah.
Yes, seventh is about the deepest you can see with the naked eye. And France has said anything that flies should be seventh magnitude or darker. The issue with this is that it is a technical challenge. It's not just about wanting to do the right thing. It's about actually being able to do it technically. It's been a real design difficulty because of all of the trade-offs that Sam mentioned.
Yeah. Sam, did you want to comment on anything else in terms of I mean, there was technical difficulties with the CCD technology that you were talking about, but there's actually, gumption behind trying to find kind of some other technical solutions from the operator's perspective, and then that opening up that conversation with astronomers for follow through.
I mean, there's also lots of image processing. That's what I do. That can be advanced in terms of different algorithms, machine learning, AI, in order to identify the effects and try and remove them. Unfortunately, if it's saturated, there's not really much you can do to recover any data. It's just flatlined essentially. So one of those why seventh magnitude is what they asked for, what they legislated, is anything fainter than that and that's moving fast enough will, for a certain telescope, not saturate. It'll spread out the light enough that there will be some recoverable data left behind. One other thing that I want to mention is this isn't just a ground-based astronomy problem. The classic solution is just put your telescope in space. And while I'm a big proponent of putting telescopes in space, that isn't a solution to this. It's very expensive. You can't service them nearly as easily. The technology level of a space-based observatory is years, if not a decade, behind what we can do on the ground. And you don't even get around the problem. The images from Hubble Space Telescope are still affected by satellites. It's not as big a problem, but they are certainly still in the data.
Interesting. Plus, you don't get all the great stargazing, right? Like I mentioned, these designated places around the country and around the world that are dark sky places. They're designated by, is it Dark Sky International?
Yep. But I think you bring up something really important that, if I was to put away all of my logical thinking and just think as a human for a moment, part of the reason Dark and Quiet Skies means so much to me as a person, the reason it got me off my couch to do something is because I thought about the fact that there's nowhere you can go on this planet anymore that is actually away from man-made objects. And that's one of the big things to consider with Dark and Quiet Skies is some people will categorize this as heritage when we talk about the heritage of a dark sky. But if you go on vacation or if you travel to a national park because you want to surround yourself in nature or because you just want to get away from it all, you want to unplug, that's not possible anymore because now no matter where you go, whether it's in a dark sky sanctuary or a dark sky park or out in the middle of nowhere in the true wilderness, you will always be able to see a satellite up above. And most of them are bright enough that you can see them with the naked eye, some very, very bright. I actually was doing, I was an astronomer in residence, kind of like an artist in residence, but an astronomer in the Central Idaho Dark Sky Reserve, which is 900,000 acres of protected dark night sky. And while I was out there, I led a lot of community Like these are literally towns that on the sign say 61 people, like truly tiny communities. And I was doing a library event, and one person raised their hand and said, "What are the shooting stars that don't go away?" And it's really interesting that, these are people who connect with their night sky every night, and they don't realize the way that it's changing very quickly. Whatever word you would use for terraforming, but the sky is how I would describe the change that we're seeing just over the last 5 or 6 years.
Yeah, yeah. I was actually in Acadia National Park up in Maine, and on the beach with the nature, the ranger talk, and was telling us about different constellations, and everyone's laying on their blanket, having a star night and stuff. And then this big bright thing,
It kind of breaks the immersion a bit, right?
yeah, it was just the solar panels reflecting.
Yeah, it's interesting because it's almost like your mind is just a million miles away, and then all of a sudden you're jarred into like, whoa, that's right in my face. Or sometimes they even look like bugs for a second. I'm like, what is that thing crawling across the sky?
Or like this recent craze of drone spottings. Most of them are airplanes, but some of them are satellites, that just people aren't used to going outside and looking up at the night sky and being able to see those things. Um, so yeah, and then just also just from the more dark sky perspective, just going out and looking up at the Milky Way is something that not a lot of people in the United States, or let alone the globe, are able to do just because of city lights. And it's something that really just like inspires creativity, curiosity, that is less and less accessible to people nowadays.
Right,
Which is
right.
which is why I think that talking about a balance is so important, because it's not just, superficial, and it's not just that the sky is falling, for astronomy. A balance is really important because one of the great tech advances that I had meant to bring up before when we were talking about other mitigation technologies is that, a lot of these satellites are offering internet service to places that just never had it before. And I believe,
Something like 60% of the satellites orbiting right now are communications, right?
yeah,
And that's bringing that last mile, connectivity to very rural areas. It brings it for emergency response situations. It brings it to in, war like Ukraine. Yeah.
exactly. I was reading an article somewhere that was like, this catapulted us into the present, like really important. And what's cool about some of these trade-off technologies is that areas that previously couldn't have reception because they were close to radio quiet zones, which is what we call those areas around radio telescopes that need to be radio quiet, because the sensitive nature of the instruments. A lot of the surrounding neighborhoods in these very rural areas did not have internet connection. And because of this, I think it is a box to break out of, because these companies have broken out of this box to balance dark and quiet skies. SpaceX in particular has worked on such narrow, precise beaming that they are able to provide cell or internet reception to places in radio quiet zones without disturbing the instruments themselves, which is a remarkable feat of technology.
Wow, wow. And it's showing the will by commercial companies to again to kind of respect the night sky for sure.
Yeah, I always tell
And
people, it's we're lucky in that the dark and quiet skies conversation has gone beyond the awareness stage. I think all the stakeholders are aware of the problem. It's now in the stage of creative technological advancements that we all need to put our heads together and figure out.
And
Yeah.
I was just gonna say, like, it's not just about uh, preventing these sorts of things. It's about driving technology that minimizes the bad effects while still taking advantage of all of the great uh, plus sides of space that we can all agree on.
Totally.
Right, right. And there's different ways to do that, right? It's the technology and kind of creating maybe some incentives to develop and test and understand some of the technology that can do that, like incentives that that are maybe kind of voluntary. So I know in late 2024 there was a Senate submission on Dark and Quiet Sky, the Dark and Quiet Skies Act. It hasn't moved since then, but it's the whole idea of like, this voluntary kind of good business, right? Because similar to the LEED, the LED certifications for buildings or for cities, it's like it's just good business, and it actually is a way to attract customers, perhaps.
Yeah, I have to give a shout out to Planet, the company Planet, because they are a small and mighty company who are honestly just out there trying to work on climate data, trying to work on weather data. They're trying to do real good for the planet, hence the name. And they are one of the companies who has signed into coordination agreements who are also working really hard to balance dark and quiet skies mitigation. So you have this shining, oh, shining is a bad word. You have this great example of a small company that's just trying to do good on all fronts because they do realize it's good business, but they also realize that it's kind of what their company's ethos is to do. And I give them a lot of credit for that.
Yeah, yeah. We're getting close to time. I wanted to, I definitely want to ask you guys if you have any final thoughts, any kind of key takeaways that you want the audience to have, or something that maybe, we didn't talk about. However, before we get to that, one of the things that is on my list is, I always like to look forward. And so what are some, Sam, I'll start with you. What are some emerging problems that practitioners foresee now? I mean, certainly the number of satellites will continue going up. Is there something that we should be aware of?
Something actually in the recent news, kind of related to what you're asking about, is this asteroid that was just discovered about a month or two ago. That has a few percent. It's dropped off recently, chance of hitting us. So I think it's less than 1% now. But just finding near-Earth objects, near-Earth asteroids, is greatly affected by these exact types of artifacts that satellites leave in our data. For example, in order to detect asteroids or comets or objects that are coming from interior to the orbit of the Earth, you have to observe them relatively close to the sun, which means observing right around sunset or sunrise, which is right when these satellites are most visible to the telescopes and to the naked eye. So it's not just an astronomy thing; it's a planetary defense issue. Is being able to see these things might mean detecting them early enough to do something about them. So yeah, another stakeholder is the Earth.
That's a really good point. That's a really great point. Thank you. Lindsay, how about you? What are some emerging problems that you foresee? Maybe from a policy or regulatory perspective, if you have that.
Yeah, there's a few interesting ones that have been on my mind lately. There's an interesting regulatory gap. We didn't really talk too much about the quiet aspect, but
Yes.
we do, though we in the world at large work with the International Telecommunications Union, or ITU, to slice up the radio spectrum, and then we all go home to our home countries and regulate according to those slicings, and that's really what the FCC does. And astronomy has some of these slices, but there's increasing demand on the radio spectrum for communications, direct to cell, internet, all of it. And what's been interesting is that even in these protected radio bands, there's been unintentional radio leakage from satellites recently. And part of the issue is that the electronics on board the satellites talking to themselves within the same craft are getting picked up at these other wavelengths. Yet there's no regulatory, rules as for how to communicate with yourself on board a spacecraft. It's only for communicating back and forth to Earth and into low Earth orbiters.
So it's not even the things coming down from the satellite, the information coming down from the satellite, but it's just within the the right side of the satellite talking to the left side of the satellite.
Exactly. Like its own inner dialogue is what's getting picked up.
Right.
So that's, it's a tricky question because it's not like they're trying to broadcast. It's kind of by accident. So that's also room for other tech advancements as well. How can we shield that? Another one that I love to talk about as low-hanging fruit is space situational awareness, SSA data really helps dark and quiet skies. And it's funny to talk to people who are kind of like new to the situation when I say like, well, we don't know where everything is and how fast it's going. And it's like, what do you mean? Like you're putting it up, it's all right there. Why don't we know? At this point, tracks, the TRACSS tracks system that the Office of Space Commerce is putting together has a lot to do with safety on orbit, straight up making sure satellites don't crash into each other. But if we can know where satellites are, where debris is, very much like what Sam was saying, post-processing becomes a lot easier. Was that a meteor or was that a satellite? Sometimes that's not a straightforward question, and it really helps to know where things were in time. So a lot of dark and quiet skies mitigation on behalf of the astronomers can be made a lot easier if we know where things are. So from a regulatory perspective or from a legal perspective, incentives for either providing that situational data or a place to host that situational data, publicize it, all of those would make really big strides and solve multiple problems at once.
Right. Right. And of course, if, doing it in the US doesn't mean that it's going to be done around the world, right? So it's about, developing those partnerships and everyone, all of the players across the sector kind of working together to make it a better thing.
Great
Yeah.
point. Yeah.
You've got ESA. I know there's recently been a call for a worldwide ban on what is it called? Obtrusive space advertising or advertising from space.
Mm-hmm.
In the US, it's been illegal for the last 25 years or something. But that's not going to stop another country from advertising Coca-Cola or something over top of us. So.
Oh, yeah, that's an interesting one too, right? There's no rules. And I think that also gets into a big hang up we're having kind of in the policy world is what novel means, licensing novel activity. And novel could mean changing orbit. Novel could mean just a totally new craft that no one's seen before. And you reminded me with the advertising conversation, that is a novel use of space. And so sometimes the argument goes like, well, should we license everything individually or should this be left up to interpretation? And that's where we get into all of the fun gray areas of policy that we have today.
We can bring in the lawyers for that one.
Yeah.
Okay, so Sam, we are at time. Sam, do you have a final thought that you'd like to share with the audience or some sort of key takeaway that you want them to go with? Remember, this is how stuff works, right?
Sure. Yeah. I think a few of the big takeaways that I've gotten from this are moving forward, data sharing is really important. Sharing these databases of where stuff is, and funding new technology that will help mitigate the root cause is also not just gonna fix these problems. Technology bleeds over into all aspects, and I think NASA is a great example of that. Just taking camera technology from space, and now everybody has an amazing camera in their phone in their pocket every day. So technology doesn't just drive the problem that you're trying to fix, it spreads out everywhere.
Yeah, thank you. Lindsay, how about you?
I couldn't agree more wholeheartedly with Sam's conclusions. Those are absolutely perfect. I think the only little icing or cherry on top I would add is thinking about your own relationship to the sky and darkness. Do you have a right to darkness? Do you need darkness? So when I talk to people, I always say the future is dark because I hope that's where we're going.
Very nice. Well, thank you guys very much. For me, I got out of the whole idea of how human activities are kind of strengthened, by satellites, our human activities here on Earth in terms of bringing internet connectivity and, the health and the banking and the education that goes with that, but also protecting science and protecting the heritage of, how you said, Sam, the Milky Way. Just that alone.
Yeah.
Thank you guys very much for joining.
Thanks for having us, Colleen. Thanks for letting us talk about this.
Absolutely. Thank you very much.
So, all right, everyone, for the audience, thank you very much for joining us today. We've got other How Stuff Works shows. They are on space weather, contested defense in space, and ISAM in space, servicing, assembly, and manufacturing. So be sure to check those out, the How Stuff Works. Besides the show, you can also read our deeper research from the Center for Space Policy and Strategy at csps.aerospace.org. Please follow us on LinkedIn to get notified or engage with our speakers, including today's speakers. All of the shows in this series and others are available wherever you get podcasts and on YouTube. Thank you to James Liggins, our technical director, and thank you for joining.